the session.
Okay, thank you, ma'am. So, welcome everyone. This is the third live session for the course Urban Land Use and Transportation Planning. So, in this session, we'll be discussing the problem solving questions for from module 9 to 12. So, we'll be basically discussing three major problem areas. The first being the solution methods for minimum spanning tree. Second being initial basic solution for the transportation problem, and finally the minimization cost, minimization of cost for the transportation problem. And finally, we will be solving the traveling salesman problem by the Hungarian method. So we'll start with the solution methods for minimum spanning tree. Okay, so I'll just give you a brief idea about the spanning tree, which has already been covered in the lecture. Spanning tree is nothing but it basically joins nodes. If there are maybe n nodes, then they and n minus one edges. So this constitutes a spanning tree. So if like there are two nodes, maybe one and two, and it is being joined by one edge. So this is a spanning tree. If there are five nodes, 1, 2, 3, 4, 5, and it is being joined by, let's say, four edges, then this is also a spanning tree. So this is basically the concept of a spanning tree. So the things covered in this module is that what should be the minimum total weight of the spanning tree for the graph given below. So from this graph given below, we have to find the minimum weight of a spanning tree that can be formed. So there are two algorithms by which we deal with these kind of problems. The first being the Kruskal's algorithm, and the second being the Prim's algorithm. In the Kruskal's algorithm, which is basically a greedy algorithm, we uh, we first start with an empty set of graphs. Let's say there is no graph initially, and then we first of all sort each and every edge according to the increasing order by the length. Then we start adding these edges into the set of the subgraph from the using the decreasing order, means the lowest the edge with the minimum weight is being added first. And finally, when if there are like for this graph, if you see there are nine edges, so nine edges, so we will be requiring 9 minus 1, that is 8 vertices. So once we reach 8 vertices, we stop this algorithm and we finally find our solution. So for this question, the question is, what is the total minimum weight? So we'll start using the Kruskal's algorithm, for which first of all we need to arrange arrange these vertices in an ascending order. So as you can see, the first of this is 7. So node 2 and 4 is having 7. Then it is node 6 and 8, which is 8, which has a weight of 8. Next being node 9 and 7, which has a weight of 9. Next being node 1 and 2, which has a weight of 10. Next being node 1 and 3, sorry, node uh, 1 and 3 has a weight of 10. Next being node 2 and 3, which has a weight of 11. The next node being, uh, do we have any 12? Uh, we have node 5 and 8. 5 and, no, we don't have any uh, 12. Okay. Then we have node 3, 2, 2 and 5. Okay, then it's node 3 and 5, nodes 3 and 5, which is 13. Okay, then we have nodes uh, 13, then we have node 5 and 8, which is 14. Then we have node after node 5 and 8, we have 14. Then we have node 3 and 6, 3 and 6, which is 15. Then we have also we have node 2 and 5, which is 15. Okay, so we have covered nodes 2 and 4. We have covered 7 and 9. We have covered 6 and 8. We have covered 5 and 8. We have covered 10, 11, 13, 2 and 5, 15. Okay, 15. Okay, next node being nodes 5 and 6, which is 17. 5 and 7, which is 18. Okay, okay, I missed out one node. One more node is 8 and 9 is also 15. 8 and 9 being 15. So, so here we'll have 8 and 9. 8 and 9, which is 15. Okay, and 5 and 7. Then we'll have nodes 4 and 5, which is 19. And then node 4 and 7 is 21. And finally, node 1 and 2 is 22. So now we'll start putting. Okay, another thing is that when we are forming, when we are forming the graph, forming the tree, it should not form a closed loop. So this thing also we need to keep in mind. Okay, now we'll start with the graph. So the first two nodes being 2 to 4. So this we have added, and remember we have to add 8 vertices. So this is the first vertices that we have added. Next is 6 to 8, 2, 4. Next being 2, 4. 6 to 8. Okay. Next being 9 and 7. So 9 is somewhere here. 9 and 7. This will add. Next is 1 and 3. So we'll have 1 over here and 3 over here. We'll add 1 and 3. Then how many we have added? 4 we have added. Next is 2 and 3. So 2 and 3 will add 2 and 3. Next is 3 and 5. 3 and 5. 3 and 5 is here. 3 and 5. 3 and 5 is added. We have added 1, 2, 3, 4, 5, 6. As of now, 2 more we need to add. 5 and 8. 5 and 8 will add like this. 5 and 8, 14. And finally 3 and 6 they are telling to add. Now if we add 3 and 6 over here, it is forming a loop. So 3 and 6 cannot be added. So we'll not take this. We'll not take this vertex. Next is 2 and 5. 2 and 5 also cannot be added because it will form a loop. Next is 5 and 6. 5 and 6. Can we add 5 and 6? No, it will also form a loop. 5 and 7. 5 and 7 can be added. It will not form a loop, and hence this we have now got 1, 2. One second, I'll just write this with some other letter, some other color. 1, 2, 3, 4, 5, 6, 7, 8. So we have got 8 vertices now. So now this is the spanning tree, right? Okay. So now we need to determine the minimum cost. So how are we determining the minimum cost now? We'll just add it up. So so we'll just add up one by one of all the vertices that we have selected. 2 to 4 was 7, 6 to 8 was 8, 9 to 7 was 9, 1 to 3 was 10, 2 to 3 was 11, 3 to 5 was 13, 5 to 8 was 14, and 5 to 7 is 18. So this adds up to be 7, 8, 15, 24, 34, 45, 58, 72, 90. So this is the minimum weight of the minimum spanning, is the total weight of the minimum spanning tree that has been obtained by the Kruskal's algorithm. Now, secondly, we'll uh, go for the solution by the Prim's algorithm. What is the Prim's algorithm? The Prim's algorithm says that we start off by choosing any one node as an arbitrary node. Then we check the outgoing edges of the nodes and select the one with the least cost. And same rule that if there is any the minimum the weight the edge with the minimum weight is selected, and the same rule is that we will stop the algorithm when we have obtained 8 vertices, and the next thing is that there should not be any loop that is being formed, same as we have done over here. So we'll start with 1 as the root node, maybe 1. Okay. Next we can go to 2 from here. We can go to 2 or we can go to 3. But we can see that 3 is the least node from here. So because it has a weight of 10, so we'll form 3. 3. Okay. Now from 1 and 3 we will check. From 1 we have 22, and from 3 we have to 2 11, to 5 is 13, to 6 is 15. So what we will do, we will join it with 2, and uh, so 1, 2, 3 and 2. Okay. Now from 2 we have 2 to 4 is 7, 2 to 5 is 15, and from 3 we have remaining 13, 3 to 5 is 13, and 3 to 6 is 15. So we will join 2 to 4, 2 to 4, which is 7. Okay. Now we have 4. From 4 to 7 is 21, 4 to 5 is 19. So these two are high. 2 to 5 is 15, 3 to 5 is 13. So this is the least of all. So we will join 3 to 5, which is 13. Okay, I'll just write the weights also. It will be helpful. 2, 11, and 13. Okay. Okay. Now from 3 we have 3 to 6, 15. Okay. From 5 I have 19, 18, and 14. And 17 also, and from 4 I have 21. So I think the least is 3 to 6, which is 15. 3 to 6, which is 15. Okay. Now from 6 I can join 6 to 8, which is the least as of now. 6 to 8, which has a weight of 8. And next from uh, 8 to 5 is 14, which is I think the least now, but we cannot join this because it will form a loop. So we will not join this. Then we have 5 to 7, which is the least as of now. So we'll join 5 to 7. 5 to 7, which is 18. And from 7, I think the last node would be 7 to 9, which is 9. So how many have we got? 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 we have got. So this is the minimum spanning tree. I think it should look same as the last one only. We'll just check it once. Yeah, it is the same as the this one. So here also we are getting some this kind of a tree diagram, and here also we are getting the same tree diagram. So the weight will be same, which is 90, the minimum spanning tree weight, which is 90. So this is just an alternative approach, an alternative algorithm where we are selecting one root node, where one was the root node, and from there we were incrementally building up the tree. The logic being, we are branching out the trees, and we are selecting those branches which has the least weight. So this is how you can solve this kind of questions, where you are giving a minimum spanning tree, and you have to you are given a graph, then you have to find the minimum spanning tree, and you have to find the weight of the minimum spanning tree. So these kind of questions can come. So we'll go to the next set of questions, which is basically the transportation problem. So this is a transportation problem matrix. Now, what we need to do is, the first part of the question is that we need to find the initial basic solution using the northwest corner method, the least cost method, and the Vogel's approximation method. And the second part of the question is, we need to find the minimum cost of the transportation of goods from supply points to demand points. Now, this is how a transportation problem matrix look like, where D1, D2, D3, these are the demand points, and S1, S2, S3, S4 are the supply points. The first step is that we need to see if total demand is equal to total supply or not. If total demand is a total supply or not. So the total supply here is 11 plus 13, 24 plus 19, which is 43. The total demand is 6 plus 10, 16 plus 12, 18 plus 15 is 43. So here the total demand and total supply are same. This is a very basic condition that we need to, and an important condition that we need to satisfy before we proceed on with the transportation problem. If it is not so, then we need to add dummy rows or dummy columns, dummy rows or dummy columns or columns based upon the situation. So here we do not need to do anything like this. So we'll proceed with the problem. So first is we need to find the initial basic solution with the northwest corner method. So in the northwest corner method, the algorithm says that first we'll start with the allocation with the northwest cell, and the maximum allocation that can be made to this cell within the supply demand constraint has to be made, and for the other cells of the row and the column, we will strike out if it is exhausted, if the supply or the demand is exhausted, and then in the remaining cells we will make the maximum possible allocation, and then repeat this until the total demand and the total supply is satisfied. So we will start with this. So here you can see, okay, northwest corner, basically if we draw a compass, north, east, south, west. So northwest corner is this direction. So basically this cell is the cells which are lying in this part, in the top left corner. They will be the top left corner. They will be the northwest cells, top left corner cells. So we will make the allocations over there. Okay. So now if we start with this cell which has D1S1, we can see the total supply here is 11. So we can make a allocation of 11 over here, but we have a supply constant of 6. So we can make an allocation of 6 only over here. So once we make an allocation of 6, this demand, this supply strikes out, this demand strikes out. Okay. Actually, this will be total demand. This will be total supply. Okay. So this supply strikes out, and this demand is 5 remaining. So to the next northwest corner, we have to make the next allocation. So we can make an this D1S2 becomes the next northwest corner cell. Here we can make an allocation of 5. So once we make an allocation of 5 over here, this total sub this total demand is satisfied now. Now once we make an allocation of 5 to D1S2, this supply reduces to 5 now. So we have to make an allocation of 5. Which one is the northwest? Okay, so this one we can strike out these two, as we had uh, given in the step 3 and step 4 of this algorithm, that we can strike out those rows and columns where the demand and the supply is being satisfied. Okay, now this D2S2 becomes the northwest corner cell. So here we can make an allocation of 5 because the supply constant is only 5, but the demand constant is 13. So we'll go with the minimum supply constant, that is 5. So once we do an allocation of 5, only 8 remains over here and this strikes out. So we can strike this D3S2 cell also. Once we strike this out, now 8 is remaining. So northwest corner, this D2S3 becomes the northwest corner where we can make an allocation of maximum allocation of 8. So we make a maximum allocation of 8. So this will strike out and this here 4 will be left. And consequently, this will also be striked out. Cell D2S. Once this is done, we can make an allocation of 4 in this maximum allocation of 4 in the cell D2, D3S3, which will strike this out, and this will be remaining 15. So 15 and 15, 15 balances here. So this is the initial basic solution by northwest corner method. By this algorithm, we can do the initial basic solution. If someone asks that find the transport cost by initial basic solution of northwest method, then you will just need to multiply these quantities with the cost. These are the costs as given in the matrix, this being the cost. So we can just do it once quickly. What will be the cost? The cost will be 6 into 21 plus 5 into 16 plus 5 into 18 plus 8 into 14 plus 18 into 4 plus 15 into 41. So this comes out to be somewhat 126 plus 80 plus 90 plus 14, 8 becomes somewhere around 112 plus 72 plus 615. So this will be your cost. So this adds up to be, I think, around 206, 296, 308, 408, 480, 480, 1095. So this is your initial transportation cost. That is coming. So we will move on to the least cost method. Now the least cost method says that we should start allocation with the cell at the cell with the least cost. This is the catch here, that we will now start the allocation like there we were doing with the northwest northwest cell, northwest corner cell. Here we will do with the least cost cell, and and other all rules remain same, that the maximum allocation is made with the supply demand constraint, and the rows and the columns will be strike out, and the repeat until all the demand and constraint or demand and supply is satisfied. So we will start. So if we look in this, the cell with the least cost is cell number D1S4 13, D1S4, which is the cost of 13. So here we can make a maximum allocation of 11 based upon the supply constant. So we will make an allocation of 11 and we will strike this out. Now all these cells will be striked out and this will be reduced to 15 minus 11, 4. Okay, now we will look for the next least cost cell, which is 14. This cell, that is D2S3. So in this D2S3, the maximum allocation that we can make is of 12 because of the supply demand, because total supply constant. So we will make an allocation of 12. So if we make an allocation of 12, now this is totally striked out. This is striked out to 1. So 1. And next we'll now look for the next least cost cell, which is most probably 17. So in 17 we can make a maximum allocation of 1 based upon the demand constraint. So we can strike this 1 out and we can strike these cells out. Okay. So the next cell where we can make the allocation is basically 27, where we can make an allocation of 10. Once we make an allocation of 10, this becomes 9. So the next is 32, where we can make a maximum allocation of 5. So this becomes 4. And the next is 41, where we can make a maximum allocation of 4. So this will be striked out and this will be striked out. So it is the initial basic solution. Initial basic solution using least cost method. Least cost method. As you can see, this is a little bit different from the northwest corner method, the solution that has been obtained. So we can check the initial cost that has been obtained once, just for the sake of that. So the cost would be, transportation cost would be 11 into 13 for this, then 12 into 14 plus 1 into 17 plus 5 into 32 plus 10 into 27 plus 4 into 41. 1, 2, 3, 4, 5, 6. Okay. So this comes out to be some 143 plus 168 plus 17 plus 160 plus 270 plus 164. So this adds up to be somewhere around 312, 472, 489, 489, 689, 759 plus 143 is 902. If I'm not wrong, 902. So this is giving a solution which where the initial basic solution is lower than the northwest quadrant method. So this is something that you can just note. Next is the Vogel's approximation method. So in the Vogel's approximation method, what is happening is we are first calculating the penalty for each column and each row. The penalty is the difference between the least of the two values in the row and the column. Then we are choosing the row or the column with the maximum penalty, and in that row or the column, we are making the allocation in the cell where there is the least cost. Then all the rules apply as same, that the allocation would be made according to the demand and the supply constraint, and it would be done until all the demand and supply has been satisfied. So in all the three methods, these are the three methods in for choosing in which cell we want to make the allocation. So these three algorithms charts out the ways in which we are choosing the first in which we are choosing the cell in which we will be making the allocation. So what it was saying, we need to first calculate the penalties. So how are we calculating the penalties? For this first iteration, we'll call this as iteration 1. What will happen is we will have to make the allocation. So if we row in the if we look up in the first row, the least cost cell is 13 and the second least cost cell is 16. So the penalty here would be 16 minus 13. 16 minus 13 equal to 3. So the penalty here would be 3. Similarly, in the next row, the least cost cell is 14 and the next least cost cell is 17. So it would be 17 minus 14, 3. In the third row, the least cost cell is 18 and the second least cost cell is 27. So it would be 27 minus 18, which is 9. Now looking at the columns, for the first column under S1, the least cost cell is 17 and the second least cost cell is 21. So it will be 21 minus 17, 4. For the column under S2, it will be 18. 16 is the least cost cell and 18 is the second least cost cell. So 18 minus 16, which is 2. In the S3 column, it is 14. 18 minus 14 because 18 is the second least cost cell, 14 is the first least cost cell. So it will be 4. In the column under S4, it will be 13 is the least cost cell and 23 is the second least cost cell. So it will be 23 minus 13, which is 10. Now what the algorithm says? The algorithm says that choose the row or the column with the maximum penalty. So this is the row or the column. This is the row with the maximum penalty. And here we have to choose the cell with the least cost cell. So here the least cost cell is 13. So the first cell that we are choosing is 13. Here a maximum allocation of 11 as we know can be made. So here we'll make an allocation of 11 and we'll strike the other cells of this row out. And here we'll be left with 4. Now again we have to recalculate after this allocation has been made. Again we have to recalculate with the remaining cells. So we'll be we have to recalculate the penalty with the remaining cells. As it's written here, strike out the column. In the remaining table, recalculate the penalties. Okay, so we'll strike these penalties out because now these are not needed. Okay, so in this will be now my iteration. Okay, so now what are the penalties? Let me just check. Okay, so in this row, this would be 15. In this row, this will be 15. In the next row, this would be 18 minus 27. This would be 9. In this column, this would be 4. And this column, this will be 18. In this row, there will be no further allocation. In this row, there will be the least is 14 and the next least is 17. So 3. And in this row, this D3 row, it will be 18 minus 27, which is 9 again. So now again, this row is coming out to be the having the maximum. So here we will make with the least cost to the least cost cell, that is 23, which is D2S4, and we'll make an allocation of 4. So we'll strike this out for 9 and this will be striked out. So this row we can strike out. Okay, this is our iteration 2 complete. Now we will do iteration. Now we'll do iteration 3. Again, we'll start with D2. For row number D2, the least cost now is 14 minus 18, so this becomes 14 minus 17, so this becomes 3. This becomes 3. The next one is 18 minus 27, so this becomes 9. For S1, it's 15. For S2, it's 9. For S3, it's 4. So now 15 S1, here we have to make the allocation. So here the least cost cell is D2 S1. So here we can make a maximum allocation of 6 based upon the supply constraint. So we'll make a maximum allocation of 6 here and we'll strike this. Again, we have to recalculate now the penalty. So here it is coming out to be 4. For D3 row, it's coming out to be 9. It stays. For S2, it's 9. And for S3, it's 4. So these two states, so 9. So now we have to make an allocation to of 9. So 9 we have D3 and we have S2. So in any one we can make. So we can make in this S2 row. So here 18. So here, sorry, here one more thing is there, that this 3. This becomes 3. So now, and this is striked out. So now we'll allocate 3 over here and we'll strike this out. Okay. So now only these two are left. So whatever allocation will happen here only. So here we will allocate 12. So what will happen? 7 will be left, and similarly 7 is left here also in S2 constant. So we'll put 7 over here. So we have made the allocations by the Vogel's approximation method. This is after iteration 4. So 4 iterations we had to do to complete the Vogel's approximation method, where we have now completed the allocation of the goods to from different demand points to the supply. Now, here also we can find the total transport cost. So you can do this yourself, as we have discussed earlier. Now what we need to do is, we need to find the solution for the minimum transportation cost. So the final solution that we have found out using the Vogel's approximation method, we'll just first write it down. So the final initial basic solution is 11 over here. Then I guess it's 4 over here. Then we have 3 over here and 6 over here. Then we have 7 over here and 12 over here. And all the cells are blank. So now for finding the solution for minimum transportation, what we do, we first find a value called ui and vi, as it has been discussed in the lecture. Once we find the ui and vi, we need to find out the cost, the zj cost of every cell, which is basically the cost of that cell minus ui plus vj vi of that cell. So this is how we will find, and if this remains positive, then we know that in that cell no more allocation can be done, and if it is negative, then we have to move our allocation to a more optimal cell. So now we'll first find out the ui and the vi. So ui for this, if we consider ui for d1 to be 0, then v4, because s4 would be s4, the value would be u1 plus v4. So the cost of s4 is 13. S4 is 13, so ui plus v4 has to be 13. As ui is 0, so v4 has to be 13. As soon as v4 is 13, now similarly S4D2 is 23. So U2 plus V4 is the cost of D2S4. So 23 minus 13, U2 would come out to be 10. As soon as U2 comes out to be 10, V1 D2S1 is equal, D2S1 cost is equal to 17, which is actually equal to U2 plus V1. D2S1 का cost is equal to 17, which is actually equal to U2 plus V1, which is U2 come out to be 10 plus V1. So V1 comes out to be 7 for us. Once V1 comes out to be 7 for us, also we can calculate the cost of V2, the value of V2 will come out to be 8. As soon as V2 comes out to be 8, U3 will now come out to be 19. And as soon as U3 comes out to be 19 now, similarly, you can see by this logic, V3 would come out to be minus 1. So now these are our U1 and V1 values. Now one by one, we will check the cost of each cell and how this kind of, and where the allocation can be made. So basically, D1 S1 Z J D1 S1 is equal to 21 minus U1 plus V1. U1 is basically 21 minus 7. So this is 14. 14 is a positive number. So 14 is a positive number. So here no more allocation can be done. Similarly, we will find the for D1 S2 where no allocation is met. So for D1 S2, it would be U1 plus V2, which is around 8. 16 minus 8, which is 8. Again, this is coming to be positive. Next, we will do for D1 S3. So it's 25 minus it's minus 1 plus 0, which is equal to 26. So again, this is positive. Now we will do for D2S3 where no allocation is made. So here it is basically 14 minus 10 minus 1, which is equal to 14 minus 9, which is equal to 5. So this is also positive. Now we will do for D3S1. D3S1 is 32 minus 19 plus 7, which is equal to 32 minus 26, which is equal to 6. Okay. Now for D3S4, D3S4, it's equal to 41 minus 19 plus 13, which is equal to 41 minus 32 is equal to 9. So this is also positive. So since all the zj values have come out to be positive, so this is the optimal solution. So the initial basic solution of the uh, table that we found using the Vogel's approximation method has come out to be our optimal solution. So now we will just find out the minimum transportation cost, which is equal to 11, which is basically the part B of our question. So 11 into 13, we are finding out the minimum transportation cost now, plus 23 into 4 plus 18 into 3 plus 17 into 6 plus 27 into 7 plus 18 into 12. So this comes out to be 143 plus 92 plus 54 plus 17 6 is 102 plus 27 7 is 169 189 plus 1812 is 216. So this is coming out to be 189, 216 is 405 plus 102 is 507 plus 54 is 561 plus 92 is 563, 90, 653, 653 plus 140 is 796. So 796 is basically our minimum transportation cost for this problem. which we did not find actually using the Vogel, the least cost method, the first iteration of the least cost method or the last best corner method, but we found it in the first iteration of the Vogel's approximation method. So this is how you can tackle the problems of these kind, where you are given a table with the demand and supply and the transportation costs as given. These are the transportation costs. And finally, you have to find out the minimum cost of transportation of the goods. We'll quickly move on to the third problem that I was supposed to discuss today. So this is using the distance method. This is basically from the class of problem of transportation. Uh, sorry, not transportation. Sorry, my mistake. This is the traveling salesman problem. The traveling salesman problem, where we need to find out the least the least cost path to travel all the cities and come back to the first city. So here we have four cities: A, B, C, D, A, B, C, D. So now, what the traveler has to do, he has to traverse through all the cities and come back to the first city with the least cost path. These 4, 6, 7, these are the distances or the cost to from maybe city A to city A to city A to city A to city B is 4, A to city C is 6, like this. And you can notice that in the cities like A to a value of m has been given. M is a highly infinite value. M is a highly infinite value because it is impossible to travel between a single city. From A to A, we cannot travel. So we have substituted this matrix with the value of M. Now, the method that we use to solve this kind of problem is called the Hungarian method, where we have the origin destination matrix of the cities. From there, we do first a row minimization exercise. Then, where we subtract the minimum value in the row of all the from all the elements in the row, then we do a column minimization exercise where we are subtracting the minimum value in the column from all the elements in the column to the from all the values of that column, and then we do the zero values that we identify. We select the least number of zero values that has been generated in that matrix. So we'll start with the row minimization exercise now. Row minimization. So in the first row, 4 is the least. So we'll minus 4 from each of these values. So we will get 4 minus 4 0, 6 minus 4 2, 7 minus 4 3. In the second row, we have 5 as the least value. So we will do 6 minus 5, 7 minus 5, and 5 minus 5. So 6 minus 5, 1, 7 minus 5, 2. 5 minus 5 is 0. Then we'll do 6, we'll negate 6 from this row C. So it will be 7 minus 6, 6 minus 6, 6 minus 6. It will be 10 minus 6, 1, 6 minus 6, 0. Again 6 minus 6, 0. And then we are not negating from the m values because m is an infinity, so infinity value. So whatever we negate from infinity, it will remain as infinity only. Still, I'm just writing it. And the next row, it's 4. So we will negate 4 from each of these values. Will be 5 minus 4, 4 minus 4, 6, 5 minus 4 is 1, 4 minus 4 is 0, and 6 minus 4 is 6 minus 4 becomes 2. So this is now the matrix after row minimization that we have got. Okay, so after row minimization, what matrix did we get? We'll just replace the values once from here. Then it would be easy. So it will be 0, 2, 3, 0, 2, 3. Then it would be 1, 2, 0, 1, 2, 0. Then it will be 1, 0, 0, 1, 0, 0. And next is 1, 0, 2. 1, 0. Okay. So now we'll see for column A. Column A, the least cost is 1. So we'll negate 1 from every column. So it will all will become 0. 1 minus 1 all will become 0. Next is from column B, it is 0 only. So everything will be 0. So all will become 0. From column C, it's I think it's coming out to be 2. So it will be all will again become 0. And then from column D it will be 3. So again 3 will be negated from all. So it will actually become 0 again. So basically everything has now become 0. I'll just check once if there was any mistake or not. 3 minus 5 was 0. 0, 6. Yeah, so this is the, yeah. So now we have got all 0. Now we just have to select make selections of from where we have to means in which city we need to allocate. So basically, if it would have been helpful if some of the values would have been 1, but let's just do one hit and try. So if A to C, if I select this 0, then this row will go, this column will go off, and this row will go off. So A to C. Next, we will from C to, let's say from C to we can go to A. So let's say from C to B we will make an trip. So C to B, the column will go off. Now once we reach B, we can select B to D, B to D, because we cannot go back to A. So we will select B to D, and then this D column will go off. And finally, we have just D left. So B to D, and then D is left. So B to D will come, and then it is back to A. So the least cost path will be A to C to B to D to A. So from A to C, what was the cost? So we'll just write here A to C to B to D to A. So the cost from A to C is 6. Then C to B. C to From C to B is 6 again. A to C to B to D is 5. B to D is 5. Then D to A to C to B to D to A. D to A is 7. So this comes out to be 12, 12 plus 5, 17, 20. So this is the least cost path that we have. So this is how you can tackle if a distance matrix is given and four cities or 5 cities are given. This is how you can tackle a traveling salesman problem using the Hungarian method. So these are basically the 3 problems that we wanted to discuss today. And just to summarize, first we discussed the uh, minimum spanning tree, how to find the total weight of the minimum spanning tree from a graph. So we did it using the Kruskal's algorithm and the Prim's algorithm. Then we had a discussion about how to find the least cost of of transportation from a cost matrix of a transportation problem, where the demand points and the supply points and the demand and the supplies are given, and the costs are also given. So from this, we first find out the initial basic solution using the northwest corner method and the least cost method or the Vogel's approximation method. And then by finding out the individual values of Zj of each of the cells, we then find which if it is the initial basic solution is the feasible and the optimal solution or not. And then we find the final cost of this cost of the transportation. So here, as we found out that the minimum cost was 796. And finally, we have discussed the traveling salesman problem using the Hungarian method, where we have used the Hungarian method and found out the least cost path between the cities in the using the distance matrix of the cities. So that's it. And one of the questions that I found in the document that was shared online, it was asked if the assignment problems are of helpful or not for the final test that we have, the final exam that we have for this course. So yes, of course, the assignment questions are very helpful, and everything, the test and everything has all been designed, and the assignment questions are also designed in line with what you are being asked in the test. So you should very religiously follow the assignment questions because it will help you a lot. The assignment questions have to be thoroughly seen, and it has to be thoroughly practiced so that you can answer the questions in the test. So that was one of the questions that was asked. So that is all from my side. And I'll just check once more if there are any more questions that has come up during this time or not. If there are no questions, then we can end the session. I'll just check and I'll, okay. Okay, so there are no more questions. So all the best everyone for your upcoming test. And I hope the video has been helpful. Thank you.
Yeah, yes. Thank you.
Yeah, thank you. So I can leave, ma'am?
Yes, yes, you can.
Okay, thank you.